So in the previous video, we had developed the first several terms of the Taylor polynomial to approximate the function natural log of x. So here in red, let me make this a little bit more bold. So here in red is the function the natural log of x. Now remember, at x equals 0, the natural log of 0 does not exist. So in fact, x equals 0 is a vertical asymptote. The natural log of 1, however, is 0, and then we see it increase concave down forever and ever and ever and ever. There you go. Now what we had done in the video is it built that the first term was actually a constant 0, does not help us, does not contribute to the success of this work. So let's start with the first non-zero term, which was 1x. And then the pattern was minus 1/2 for the x squared. And then a plus, and we had this alternating plus minus plus minus. The next term was 1/3 x cubed. And now you might already be kind of wondering, if you've been playing with this, I hope you have, you might be wondering what's going on, and maybe you're seeing something. That as the terms increase, it kind of follows the pattern of this red natural log of x function, but it kind of does so like off by a bit, like shifted to the left, the blue function is, just a little bit. Well, let's just see what happens if we keep going. We saw that the next term was 1/4 x to the 4th, and we saw that the next term would have been a plus, or we didn't build this one in the video, we just see the pattern now and we just start going for it. And I hope now you see that as we continue to build terms, that we do get a little bit better of an approximation, but still kind of shifted to the left. That wasn't good. Yeah, what is that about? Well, maybe you figured it out, but been kind of making it a cliffhanger here for you. What's going on? What's going on is, remember, we had to shift, or we had to center our work around x equals 1, not x equals 0. So we need to shift this blue function to the right 1 unit. Let me remind you of some algebra. If you replace the x with x minus 1, yes, x minus 1, that shifts the entire polynomial to the right. X minus 1 shifts the polynomial to the right 1 unit. Horizontal shift, not going to explain that at this moment. But let me replace all of those x's with x minus 1 to demonstrate that shift of 1 unit to the right. And I hope now you can see it already happening, that the blue Taylor polynomial approximation is indeed converging upon the red natural log of x function. The more terms in the Taylor polynomial, the better the approximation. I hope you can see it. So, let's go for it. Let's build the infinite Taylor series. Well, at least infinite relative to Desmos. Do you see the pattern? What we're doing is we have a sum. Did you notice what Desmos did there? You just start typing sum and it'll give you the sigma notation. We have a sum. I'm going to start counting out n equals 1. I hope you see why. This coefficient here is 1/1. So if n is 1, and then if n is 2, 1/2. If n is 3, 1/3, etc. So if I start counting at n equals 1, that coefficient of each term is just 1/n. 1/1, 1/2, 1/3, 1/4, 1/5, etc. And we're going to keep going until, well, theoretically, till we get to infinity. But I'll go ahead and make it an a for now. Let me keep building, you'll see it. And then it was x minus 1 to get that horizontal shift 1 unit to the right. And then it was raised to the power of. So if this first term is n equals 1, the power is 1. When n equals 2, the power is 2. When n equals 3, the power is, yes, it's 3. And so it's x minus 1 to the n. And then, don't forget, this thing alternates plus minus, so I'm going to need a negative 1 to the something. And you guys, you can memorize it or you can just make sense of it. When n equals 1, negative 1 to the 1 would be negative 1, turning this whole first term negative. I don't want it to be negative, so I'm going to make my exponent n minus 1. Here's what I'm thinking. When n equals 1, 1 minus 1 is 0. Negative 1 to the 0 is positive 1. Yay! When n equals 2, 2 minus 1 is 1. Negative 1 to the 1 is negative 1, making the term negative. Yay! All right, let's make a slider, and let's make, we can go from 1 to, can't go to infinity. Let's see how it goes to 100. Let's see how crazy it gets. We'll just go in steps of 1. Let's see what happens. Are you ready? So here in green, we should see, let me get rid of the blue one. In green, we should see, first of all, that y equals 1x, shifted 1 unit to the right, and then the quadratic, and then the cubic, and then the quartic, and then it's and then. Let it catch up. Now remember, there it goes. Once you get to higher values, it starts to get more difficult. But what I want you to see here is something really interesting with the natural log of x. Let's back this thing back to the beginning for a minute. And let me just zoom in just a bit, because I want you to notice something about the natural log of x Taylor polynomial approximation. Are you ready? Watch it again. There's the linear, the quadratic, the cubic, the fourth, the quartic, the quintic. And then after that, we just say 6th degree, 7th degree, 8th degree, 9th degree, 10th degree, 11th degree. Do you see it? It appears as though this Taylor polynomial for the natural log of x converges very nicely onto the natural log of x function as the number of terms grow. I mean, look down here in that asymptotic area for a minute. Do you see it get closer and closer? Converge, 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 converge. The bigger the power gets, the more it's converging. But watch out here. It seems like the convergence never gets past x equals 2. It appears as though this function, this Taylor polynomial function, converges on top of that natural log of x function only between x equals 0 to x equals 2. That's it. What's up with that? Keep watching. I'm going to share something about that.